The Higgs boson is the fundamental force-carrying particle of the Higgs field, which is responsible for granting other particles their mass. This field was first proposed in the mid-60s by Peter Higgs, for whom the particle is named, and his colleagues. The particle was finally discovered on July 4, 2012, by researchers at the Large Hadron Collider, LHC, the most powerful particle accelerator in the world, located at the European Particle Physics Laboratory CERN, Switzerland. The LHC confirmed the existence of the Higgs field and the mechanism that gives rise to mass, and thus completed the standard model of particle physics, the best description we have of the subatomic world. As scientists approached the end of the 20th century, advances in particle physics had answered many questions that surrounded the fundamental building blocks of nature. Yet, as physicists steadily populated the particle zoo with electrons, protons, bosons, and all flavors of quarks, some pressing questions remain stubbornly unanswered. Amongst these, why do some particles have mass? The story of the Higgs boson is motivated by this question. What is the Higgs boson? The Higgs boson has a mass of 125 billion electron volts, opens in nutab, meaning it is 130 times more massive than a proton, according to CERN, opens in nutab. It is also chargeless with zero spin, a quantum mechanical equivalent to angular momentum. The Higgs boson is the only elementary particle with no spin. A boson is a force carrier particle that comes into play when particles interact with each other, with a boson exchanged during this interaction. For example, when two electrons interact, they exchange a photon, the force-carrying particle of electromagnetic fields. Because quantum field theory describes the microscopic world and the quantum fields that fill the universe with wave mechanics, a boson can also be described as a wave in a field. So a photon is a particle and a wave that arises from an excited electromagnetic field, and the Higgs boson is the particle or quantized manifestation that arises from the Higgs field when excited. That field generates mass via its interaction with other particles and the mechanism carried by the Higgs boson called the Brout-Englert-Higgs mechanism. Why is the Higgs boson called the God particle? The Higgs boson's nickname, the God particle, was solidified upon its discovery, namely as a result of the popular media. The origin of this is often connected to Nobel Prize-winning physicist Leon Lederman referring to the Higgs boson as the goddamn particle in frustration with regards to how difficult it was to detect. Business Insider, opens in new tab, says that when Lederman authored a book on the Higgs boson in the 1990s, the title was to be The Goddamn Particle, but the publishers changed this to The God Particle, and a troublesome connection with religion was drawn, one which bothers physicists to this day. Still, it's hard to overestimate the importance of the Higgs boson and the Higgs field in general, as without this aspect of nature no particles would have mass. That means no stars, no planets, and no something which may help warrant its hyperbolic nickname. Why is the Higgs boson important? In 1964, researchers had begun to use quantum field theory to study the weak nuclear force, opens in nutab, which determines the atomic decay of elements by transforming protons to neutrons and its force carriers, the W and Z bosons. The weak force carriers should be massless, and if they weren't, this risked breaking a principle of nature called symmetry, which, just like the symmetry of a shape ensures it looks the same if it is turned or flipped, ensures the laws of nature are the same however they are viewed. Putting mass arbitrarily onto particles also caused certain predictions to trend towards infinity. Yet, researchers knew that because the weak force is so strong over short-distance interactions, much more powerful than gravity but very weak over longer interactions, its bosons must have mass. The solution proposed by Peter Higgs, François Englert, and Robert Brout, in 1964 was a new field and a way to trick nature into breaking symmetry spontaneously. An article from CERN, opens in new tab, compares this to a pencil standing on its tip, a symmetrical system suddenly tipping to point in a preferred direction, destroying its symmetry. Higgs and his fellow physicist proposed that when the universe was born it was filled with the Higgs field in a symmetrical, but unstable state like the precariously balanced pencil. The field quickly, in just fractions of a second, finds a stable configuration, but this in the process breaks its symmetry. This gives rise to the Brout-Englert-Higgs mechanism, which grants mass to the W and Z bosons. What was later discovered about the Higgs field was that it would not only give mass to the W and Z bosons but that it would grant mass to many other fundamental particles. Without the Higgs field and the Brout-Englert-Higgs mechanism, all fundamental particles would race around the universe at the speed of light. This theory doesn't just explain why particles have mass but also, why they have different masses. Particles that interact or couple with the Higgs field more strongly are granted greater masses. Even the Higgs boson itself gets its mass from its own interaction with the Higgs field. This has been confirmed by watching how Higgs boson particles decay. One particle not granted mass by the Higgs field is the basic particle of light, the photon. This is because spontaneous symmetry breaking doesn't happen for photons as it does for its fellow force-carrying particles, the W and Z bosons. This mass-granting phenomenon also only applies to fundamental particles like electrons and quarks. Particles like protons made up of quarks get most of their mass from the binding energy that holds their constituents together. While all this conforms well to theory, the next step was to discover evidence of the Higgs field by detecting its force-carrying particle. Doing this would be no simple task. In fact, it would require the largest experiment and most sophisticated machine in human history. In this way, the search for the Higgs boson itself has pushed both particle accelerator and detector technology to its limits, with the ultimate expression of this being the Large Hadron Collider, LHC. Higgs boson discovery and the Standard Model. Detecting the Higgs boson isn't just a question of setting up a detector and waiting for one to come along. These particles only existed in the high-energy conditions of the early universe. That means before detecting this particle, these high-energy conditions have to be replicated and Higgs bosons have to be created. The LHC does this by accelerating protons to near light speed and smashing them together. This creates a cascade of particles that quickly decay into lighter particles. The Higgs boson decays too rapidly to be spotted and was instead identified by detecting particle decays that indicated a particle with no spin and matched theoretical predictions for this missing boson. The particle was detected by both the LHC Atlas detector and the Compact Muon Solenoid, CMS, detector. The announcement of the detection of the Higgs boson was made at CERN in Geneva on July 12, 2012. It took until March the following year to confirm this. The detected particle was indeed the Higgs boson. By revealing this particle, predicted by the Standard Model, the discovery of the Higgs boson completed this picture of the subatomic world. There are still mysteries beyond this theory, such as the nature of dark matter, which the Higgs boson through its unique properties could help solve. The Higgs boson after 2012. The year after the discovery of the Higgs boson, Peter Higgs and François Englert were awarded the 2013 Nobel Prize in Physics, for their Higgs field theory. The Nobel Committee, opens in new tab, wrote of the award, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle, by the Atlas and CMS experiments at CERN's Large Hadron Collider. The discovery of the Higgs boson may have completed the Standard Model, but this wasn't the end of the investigation of this elusive particle. One of the major discoveries made since 2012 has involved confirmation of the decay of the Higgs. And the investigation of this elusive particle will deepen during Run 3 of the LHC, and particularly when the particle accelerator's high luminosity upgrade is completed in 2029, opens in new tab. This will allow the LHC to conduct more collisions, providing researchers with more opportunities to spot exotic physics, including phenomena beyond the Standard Model. CERN estimates that following the upgrade each year, the accelerator will create 15 million of these particles. This is compared to 3 million Higgs bosons created by the LHC in 2017. This may be key to detecting other flavors of the Higgs boson. Theories that go beyond the Standard Model of particle physics also predict as many as 5 different types of Higgs bosons, which may be produced more infrequently than the primary Higgs boson. Even before the upgrades, scientists have already provided us with tantalizing evidence of a magnetic Higgs boson.